everyone, and welcome to this Riviera-PRO video. My name is Chantel, and I'll be demonstrating the tools you can use in Riviera-PRO to find the causes of X's, or unknowns, when simulating your design. But first, I'd like to just give a brief overview on X's. X's are basically what simulators use to tell you that there's ambiguity in how the physical hardware would behave under certain circumstances. In reality, this would be a 0 or 1, but the simulator cannot predict this value as there is uncertainty. X's can also be used as don't cares, meaning that the value is not important under a certain condition. This video refers to X's behaving as unknowns. These X's can end up being quite problematic, as hardware behavior should never be unpredictable. Not knowing how the hardware will behave makes it unreliable and potentially dangerous. The other reason is that simulators can interpret these X's in different ways, causing either X-optimistic or X-pessimistic issues. X-optimism is when the X's are converted into a discrete value of either 0 or 1. This can potentially hide the cause of a bug and make debugging the design harder since the X is masked by a real value. X-pessimism is when the X's are kept and passed down through the code. This helps to show the X's and where they occur, but it can cause the X's to propagate in simulation when in reality the design would work fine. This propagation could also make tracing back to the source of the X difficult if the first observed X is far down into the code. X-pessimism can potentially cause the simulation to lock up in an unknown condition as well. So now that we know a bit about why X's can be bad, let's talk about some of the main causes of X's. Metastability or timing violations can cause X's if the signal violates the setup or hold time. There may be uninitialized variables, registers, memories, or latches where there's no reset or value setting implemented. Bus contention may cause X's to appear if different processes or components are trying to drive a shared bus at the same time. There may be explicitly assigned X's or don't cares, like in case statements. Inputs or buses might be floating in the design and aren't connected to anything. There may be multiple drivers to one reader, and there may be signals reading or accessing out-of-range arrays or vectors. Whatever the cause may be, Riviera-PRO has a number of tools that can help easily identify the origins of these unknowns. So now let's get into the example design. So here I have Riviera-PRO's Verilog frequency meter example design open. This design is just a simple frequency meter with a state machine for control, a BCD counter, and a 7-segment LED display to show the measured output frequency. It already has a macro that does all the appropriate setup and compilation, as well as simulation. I've also made some changes to this design to cause unknowns to occur. So, that means we'll be using the tools I will talk about to find the cause that I put into the design. Before we can run this, go to the design's properties, and inside of the general simulation settings, make sure the generate debug data and generate data for Dataflow options are enabled. Make sure to click apply, and then OK. And now I'll introduce the first tool to help us find the causes of unknowns called Xtrace. This tool will trace specified signals during simulation and will keep track of any unknowns it comes across. Xtrace can be set to pause simulation when it comes across an unknown, or even log the results in a file. As long as debug is enabled from either compilation or simulation, Xtrace should work. But if debug data isn't enabled, go back to the properties, and back to simulation, general, and click on enable Xtrace. Then under the Xtrace subsection, I will change the parameters and reporting settings. I'll enable Xtrace to stop when it finds an unknown, as well as allowing cross-probing with Dataflow, listing the drivers of the signals with unknown value, and printing a list of items found by Xtrace. Now save the changes and run the macro. With the simulation initialized and my signals added to the waveform, I'm going to add a signal to Xtrace by right-clicking. I'll do LEDD for this example, and go to Add to Xtrace. The console shows that the signal is now traced, and so now let's go ahead and run the simulation. And it looks like simulation has stopped at an unknown. In the console, thanks to the options that were set, we can see the Xtrace log. It shows that the LED got an unknown at 186.5 microseconds, and the driver that was causing this comes from this assigned statement. Now I'll just continue to run to the end. Now with the simulation finished, I'm going to talk about the second tool, that is the Waveform Viewer. In this viewer, any of the X's that occurred during simulation will be indicated with a solid red bar spanning from the start to the end of its occurrence. This tool helps to visualize where and when the unknown occurred in simulation, and can help find the possible causes of the unknown based on the other signal's waveforms. This viewer is also capable of cross-probing with other windows and tools, like how you saw earlier with me adding a signal to Xtrace. And now, speaking of cross-probing, I'll use the Waveform Viewer to cross-probe with our third and fourth tools, the Advanced Dataflow window and the Drivers and Readers window. I'll reset the simulation, add LEDD back to Xtrace, and also add it to Advanced Dataflow and to Drivers and Readers. Now we have our two windows together. Dataflow displays the visual connectivity of the simulated design. This is super helpful because this can be used to visually trace back to the cause of an unknown while seeing how the signals are connected. The Drivers and Readers window performs a similar task where you could see a list of what's driving the signal and who's reading the signal. This can be used to trace how the LED got its value. Double-clicking the driver or reader will display its declaration source, and from there, you can right-click on a signal in the HDL editor and add it back to the Drivers and Readers window to continue tracing. Now to demonstrate the Dataflow window. As a quick note, with our settings, you can cross-probe Xtrace with Advanced Dataflow by right-clicking on the Xtrace object and selecting Add to Dataflow. I'll click on Run to reach the unknown again. Now we can see how LEDD has gotten its unknown. One neat way to help with visually tracing the cause of X is by toggling gray mode, and then right-clicking the signal and clicking on X-Way. This will continue to trace until it finds the source of the unknown. But as we can see, the X's go even further back than just that LED. And even after more tracing, there's still more X's. So since this can become a tedious task, especially if this design was more complex, I can now introduce what is likely the most crucial tool for unknowns called Cause Finder. As the name suggests, this tool helps to find the cause of the unknown through a visual flowchart that presents all possible sources of the unknown. As a cautionary note, the Cause Finder will work only if Dataflow is enabled. Using LEDD again, I will right-click in the Dataflow window and select Find Xcause to open the Cause Finder window. Here, you can change the orientation of the graph by disabling vertical view. You can also choose to ignore intermediate value changes and group objects by time. In each of the enclosed objects are their names, the time of occurrence, and the symbol representing their type within the design. The diamond-shaped object at the end is the object containing the unknown. As we move upwards, the rounded rectangular object at the beginning of the graph is the object causing the X propagation. Objects in between the beginning and end objects also contribute to the propagation. The arrows represent objects that can contain possible sources of X's. Double-clicking on any of these objects will lead you to their instantiation in the HDL editor. We can see that LEDD got its value from this LED assignment. Going back more, the hex value got its value from BCDT, which gets its value from BCDTI. Then, this signal gets its value from count, where count gets its value from count_i. And finally, we have the process that caused count_i to get an unknown, which looks like it's coming from itself. Looking at the always statement and looking for where count_i is assigned, I see that count_i has two non-blocking assignments, both of which use itself as part of the assignment. And now, we've finally found our culprit. I'll comment out the count_i assignment on line 36, save the change, stop simulation, and rerun the macro. I'll add LEDD to Xtrace and advanced Dataflow once again. And finally, let's run the simulation. And there it is. Xtrace and advanced Dataflow are free of X's, and attempting to add LEDD back to the cause finder only tells us that there's no undefined value to look at. As you have just seen, the cause of the X in this video was one of the many ways X's can occur in hardware design. And as we saw by the simulation results and tools, those X's can be problematic and can lead to unpredictable behavior throughout the entire hardware. But with these Riviera-PRO tools that I just demonstrated, finding those unknowns will be light work. Using their strengths together, or even just individually, will help to catch the culprit or culprits of the X's before they catch you. And that concludes this video. Thank you for watching.